Here's another conservation of energy problem, pretty classic one here. What you have is a skier, height h0 above the ground on a ski slope, and they're going to go all the way down this slope here, and they're going to end up at this position right here, which is a height h1 above the ground. Here's where the skier will be right here, height h1 above the ground. And what you'd like to know then is when they're launched off of this ramp here, how far are they going to go? How far are they going to sail through the air before they hit the ground again, say maybe some distance delta d, sort of like a ski jump. So it's a pretty classic conservation of energy problem. Let's just get it set up. In particular, I'll note here that E initial is equal to E final. So the initial energy of the system should be equal to the final energy of the system. And I'll say that the skier sitting up here on top of the slope, there's their initial energy. Their final energy is going to be right here. And so really, if we want to know how far they're going to land, they're going to launch and sort of be in the air right here, what we'd like to know is this velocity right here. We'd like to know what speed they leave the ramp with. If we know what speed they leave the ramp with, then the problem can really be reduced to something we've done much earlier in the quarter, which is something like a projectile motion problem, and all the usual things can apply there if we can just find this V here. So go ahead and set up the initial energy. Looks like they just have potential up here because the problem notes that they're at rest. There's no kinetic up here. They're just sort of waiting up there for the release, and they go. And over here, they definitely have some, in the final case over here, this is an equal sign, they definitely have some final potential energy, mg times h1, and they have some kinetic energy in there as well, 1/2 mv squared. So they're definitely moving when they hit here, when they hit this point here. They're not at rest. And so the initial potential energy they had at the very top of the slopes equal to the potential energy they have right here at this sort of lower level right here, plus their kinetic energy. So from this equation right here, you could definitely just solve this for V here, and you'll get some number for that here, which will sort of tell you this will be their launch speed. And if you look very carefully at the problem here, if you know this angle in here, which you can figure out from the problem, this is some angle alpha here, then they're launched from this height h1 with this V and that theta right there. So you can sort of think of the problem like this. You can think of them as being on sort of a surface like this here, and this surface here is a distance h1 above the ground, and here's the ground over here, and they're being launched like this with some speed V at some angle alpha like that in projectile motion. So now you want to just see how far they're going to go here to get your answer to the problem. This will be some distance d. That'll be the answer to the problem you want. So you should probably know how to do this from some things that we did weeks and weeks ago earlier in the class, but it's a straight projectile motion problem. The first thing you should probably figure out is the hang time, the delta some hang time, and that'll come from something like this. If you know they start at a distance h1 above the ground, or excuse me, they end up on the ground, given that they started from a height h1 above the ground, their initial upwards velocity here is v times the sine of alpha, and of course they're being pulled down by gravity, minus 1/2 g times delta t squared. I guess there should be a delta t in there too. So this is just y is equal to y naught plus v0 delta t plus 1/2 a delta t squared, one of the kinematic equations. For either case, if you solve this thing here, it looks like it'll be a quadratic. You'll get delta t, and that delta t will be the hang time. And you should know how to solve the problem from here, because if you want to know their range now, then you can say, well, their distance d is just going to be their x component of that launch velocity, which is going to be v times the cosine of alpha times delta t, where this delta t is that hang time. So it sort of goes down to projectile motion problem. So nice kind of problem. Combine some ideas of conservation of energy to get the speed here with some kinematics and good old projectile motion at the very end there.